Hello, everyone. We're on section 7.3 today. Nice, short, little, quick, easy little section for you today. This is the one I mentioned yesterday, or the binomial distribution, the connection. There's one that's similar. This is called a geometric distribution, sometimes also called a waiting time problem. So the question would be something like that. What's the probability that there will be at least 3 flips before we get the first head? Or something like, what's the probability we get the first head on the 7th flip? That sort of thing. So it's got some conditions. It's called a geometric probability distribution. It's got 4 conditions, just like the binomial. It's going to feel a lot like the binomial because it is binomial. It's success or fail. They need to be independent, just like the other one. This one, the only minor difference is this time that trials continue until you get the first success. Once you get the first success, we typically stop. So remember, in the binomial, there was a fixed number of trials. So in the binomial problem, we would say something like, what's the probability of getting 3 out of 8? In this case, we would say, what's the probability of having the first success on the 8th trial? A little different type question. And then the probability of success is the same for each trial. I'm going to give you the formula, and we'll just kind of go through one. This time, the random variable counts the number of trials until the first success. So K is how many trials you get the first success. The formula is 1 minus P to the K minus 1 times P. So for instance, I'll give you a basic one. I'll come back to that in just a second. So let's just go, if the probability of success, let's say, is 0.3, then I say, what's the probability we get the first success on the 5th trial, let's say. So notice one thing that's missing here. There's no n choose r like there was in the binomial. Otherwise, it looks kind of similar, right? The reason there's no n choose r this time is because there's no rearranging, right? In the binomial, we could rearrange how to get those 3 heads. In this case, it's got to be, for this one, first success in the 5th trial means 1, 2, 3, 4, 5 means we fail, we fail, we fail, we fail, and then we succeed. It's the only way for it to happen. So this would be 0.7, 0.7, 0.7, 0.7, 0.3, 0.7 to the 4th times 0.3. This is the formula you see here, right? Q to the K minus 1. So whatever trial we want that first success on, we have to have failures up into that, and then just the one little P, right? Just the one little P every time. We can learn some stuff about mean, standard deviation, that sort of thing too. This time the mean is 1 over P, and this is the mean would be the expected number of trials until you get that first success on average, right? On average. So think about if we're flipping a coin, the probability is 1/2. 1 over 1/2 is 2. What that means is on average, if I flip the coin, I would get my first success. Remember, I'm going to stop when I get the first success on the 2nd trial. So my flip, I get a head, I got the first success, I'm done. But it might be a tail and then a head, or it might be a tail, 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 tails, and then a head. The idea is on average, it's going to take me 2 times. Sometimes we'll get exactly 2. Sometimes the average doesn't come out exact either, right? It's just an average. And then if you go back to my original problem, the last thing, the mean, 2 more things, and then the example. The standard deviation is the square root of Q over P. So sometimes we write this as the square root of Q over P. Just something to know, it's just a formula base. And this time the distribution will always be skewed right, which I hope makes a little bit of sense because you're going to see the higher the probability of success, the difference the skewness changes. But it's always going to be skewed right because it's going to be less likely to get like 8, 9, 10, 11, 12, 13 trials until your first success. So let's go back to this first problem where it says, just because this is a little bit different because I got this at least, right? What's the probability of at least 3 flips before we get the first head? Probability of at least 3. So I'm going to do before first head. So I'm going to do what we've done before. I'm going to think about it this way. This time there's no 0, by the way. You can't have 0 successes. Remember, you can have 0 successes, but this is the number of tries until we get the first success. So 0 is not going to happen. 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. This theoretically can go on indefinitely. At some point, they're going to be really, really small, basically 0. This time, my probability of success is 0.5, right? So to get the success on this one, it's 0.5. On this one would be 1 failure and one success. I probably shouldn't be using 0.5 because of the, let's change that actually. Sorry about that. So let's go first success, and we'll call the probability of success 0.3 like we did before. And then I clean this up here. Sorry about that. We'll go, the first one would be 0.3, or this would be one failure and then a success. This would be two failures and then a success. This would be three failures and then a success, and so on. And then depending on the question, this was at least three. At least three before. This is kind of weird wording. At least three before means I have to have the failure on the third one also. So here's the catch, though. Technically, I would want to add up all of these, right? But I can't because there's infinitely many. They come zero. But I don't really want to do that anyway, because wouldn't it be a lot easier just to add up those three and then subtract my answer from one? Okay. We usually don't ask too much higher than that, but that's the way to do it. So that's it for this one. It's pretty straightforward. There's a couple little twists in the problems you'll see, but we'll go over the homework in class and clean those up.